Okay, so we will start the portion for module 4, which is about digital electronics. Okay, so hello everyone, and today I will start the module 4 portion, which mainly covers the digital electronics part. Okay, so obviously it starts with digital signals and binary numbers and their conversion to different binary number representations, and so on. So we know that the signals which are discrete in time and amplitude domain are called digital signals. Okay, and they can assume only two values or levels. Okay, so for example we can have low level generally denoted by 0 and high level, this is generally denoted by 1. Okay, and the circuits which process these digital signals are called digital circuits, right? And hence a system developed for digital signal processing would be called as a digital system. Okay, so what are these digital circuits made up of? These are fundamentally made up of from the same elements that we use for building amplifiers also. So BJTs and FETs, that is field effect transistors, are used for constructing digital circuits. Okay, and they have numerous applications as we see around ourselves. So that digital systems are used in communication, uh, and traffic control, business transactions, spacecraft applications are there. Then in medical treatment they are used, weather monitoring, internet, and various industrial and commercial and scientific applications are there. And if we go specific, we can uh, narrow down to some very popular digital equipments like digital telephone, digital TVs, then digital cameras, and so on. Okay, so for representing these digital numbers, we have a 0 and 1. Okay, now this 0, if it is representing basically it will represent the voltage level. Okay, and if it represents a low voltage level, and 1, as usual the name suggests, if it represents uh, high voltage level, then this number system would be called as a positive logic system. And otherwise, if they are their roles are reversed, for such that 0 is used for representing high voltage level and 1 is used for representing low voltage level, then they would be called as a negative logic system. Okay, but most of the time we will be dealing with positive logic system, so that the things are straightforward. Okay, and we are also habitual in the sense that we consider that the value of 1 is higher than the value of 0. Okay, So let us start with the first subtopic, which is about binary numbers. Okay, so we know about decimal numbers, so let's first discuss about decimal numbers. Okay, it is having 10 digits, as all of us would agree, and the digits are 0, 1, 2, 3 up to 9. Okay, right, and this would be called as its digit set. So a digit set will consist of all the digits that are allowed for a particular number system, right? The radix or the base for this decimal number is 10, and this 10 is also equal to the number of digits in the digit set. Okay, so indicates that there are total number of 10 digits in its digit set, right? And every digit has got a certain weight, so this is a weighted number system. So this is also a very important point for binary, sorry, for a decimal number representation, that every digit is having a certain weightage. So for example, okay, if the number is 1437 in decimal, okay, so 10 is to denote its base, that this is a number system having base 10, which is a decimal number 1437. So the value of this number can be calculated from the value at each, from the digit at each of its digits present at each position, and multiplying with its weight. Okay, so for example, the weightage of this first digit is 10 to the power 0, the weightage of second digit is 10 to the power 1, the weightage of this third digit is 10 to the power 2, and the weightage of this fourth digit is 10 to the power 3. So we can go like this: 1, the value into its weight, plus 4 into its weight, plus 3 into its weight, plus 7 into its weight. So this will be 1000 plus 400 plus 30 plus 7, and this will result in 1437. Okay, so the point to remember is that each digit is having a certain weight, and this will be decided by the radix of that particular number system. Okay, so similarly, going down for binary number system, so in similarly in binary number system, as we know that there are only two digits, 0 and 1, so this is its digit set. Okay, and the radix or the base for this number system is 2, so that also represents that the number of digits in its digit set would be equal to 2. Okay, and this is also a weighted number system, so the decimal number system was there, so this is also a weighted number system. So we can take a certain example. For example, yeah, we can represent 6 in decimal like this: 1 into 2 to the power 2 plus 1 into 2 to the power 1 plus 0 into 2 to the power 0, and you calculate and sum up these terms, you will get 6. Okay, and the weight for each digit is this one, 2 to the power 0, the radix to the power, okay, 2 to the power 1 and 2 to the power 2, and it will go like this for each digit location. And we collect all these ones and zeros associated with each term, and we get 110, and this is the binary equivalent number for this particular decimal number, which is 6. So I can write like 6 in decimal is equal to 110 in binary. So this conversion is there. Can we will also see this conversion in detail by a different method, but right now the point is that we can convert one number into a different number representation. Okay, then a binary digit, or the 0 and 1s, they are also known as a bit. Okay, each of these 0 and 1s are called as individual bits, and group of 8 bits would be called as a byte, and a group of 4 bits would be called as a nibble. Okay, so with this background, let us start and see how to represent different number or decimal numbers into a binary number system. So let's first see decimal to binary conversion. Okay, so the idea is to divide the decimal number successively or progressively by 2 till the remainder becomes smaller than equal to 1. Okay, and collect all the remainders to get the desired binary number. So it will be better understood with one example. So the task, suppose, is to convert this 23 in decimal, what it would be in a binary. So like I said, the method is to divide this number continuously by 2 and collect all the remainders. Okay, so we know that 2 into 11 would be 22, and the remainder left is 1. Okay, now again 2 5s are 10, the remainder is 11, sorry 1. 2 2s are 4, the remainder is 1. 2 1s are 2, and the remainder is 0. Okay, and move backwards, collect all these remainders 1 0 1 1 1, and it will give you the required equivalent binary numbers, which is equal to 23. This can also be verified, like if we start from here. Okay, the least significant bit, this would be 1 into 2 to the power 0 plus 1 into 2 to the power 1 plus this one plus 1 into 2 to the power 2 plus 0 into 2 to the power 3 plus 1 into 2 to the power 4. So this becomes 1 plus 2 plus 4 plus 16, which is nothing but 23. So this is the correct answer. So once you get the equivalent binary number, you can verify your answer by using this method. Okay, so this is the method, a very simple straightforward method by which we can convert a decimal integer, basically a decimal integer number into its equivalent binary number, right? So like you can practice. So the task would be to convert following decimal number into binary. So let's say I give 25, then 576, then 1024, then I'll give 2048, then let's say 999. So you can practice with the by taking certain numbers. Okay, but what about when the decimal number is not an integer number, when it is a fractional number? So when the decimal number which needs to be converted into its binary numbers representation is a fraction, let's say uh, 0.75. So what is its equivalent number in binary? Okay, so idea here is to multiply this number. So we uh, earlier we divided the number, but when it's a fraction number we multiply the number continuously. Okay, so look at here, 0.75 into 2 becomes 1.5, and collect all these carries. So carry here is 1, and bring this, the remaining fractional part here, again multiply it by 2, it will become 1.0. So carry this time is 1, and we have a fraction of 0, so it will result 0 again. So we can stop here. Once we get a 0 at the fraction part, we can stop there, and coming from this position we can collect the carries, and we can write that 0.75 in decimal is equal to 0.11 in binary. Okay, so let's take one more example. The task is to convert 0.55 in binary. So let us multiply this. 0.55 into 2 is equal to 1.10. Carry is equal to 1. Now the next multiplication would be with 0.1 into 2, which is equal to 0.2. So carry is 0 here, right? Next step would be 0.2 into 2, which is 0.4. Carry is 0 here. We will not stop because the fractional part has not become 0. Okay, now 0.4 times 2 is 0.8. Carry is still 0 here. 0.8 times 2 is 1.6. The carry is 1. So next step would be 0.6 times 2 becomes 1.2. Carry is 1. Okay, next step would be to multiply 0.2 into 2, and it will be 0.4, and the carry this time is 0. But again we can see that this step was repeated here. 0.2 times 2, 0.2 times 2. So again we can predict from here that the next 3 steps would be resulting in 0, 1, 1. Okay, So we can say that these three steps would be uh, repeating over and over and over and over and over again and again. Okay, so we can do one thing. Either we can stop here or we can keep doing the calculation. So it is not, but there's no point in continuing from here. So we can write that 0.5510 is actually equal to 0. This 1 1 and this 0 0, then this 0 0 1 1 0 0 1 1, and it will keep on repeating like this in binary. One thing we can also do is we can put a bar on this portion 0 0 1 1, which will indicate that this portion 0 0 1 1 will come over and over again after this. So it will be like this: 0 0.10 0 0 11 0 0 11 0 0 11, and it will go like this. Okay, so you can practice some more conversions, like 0.595 in 10 is what in 2, or in binary 0.98 in decimal is what in binary. Okay, so the point here is, if a decimal number, if decimal number contains integer and fractional part both, then what will you do? Fractional part both. Okay, find or calculate the binary equivalent separately. Binary equivalents separate and combine them to get the complete number. Okay, so you do the calculation separate for the fractional part and the integer part, and then you combine those two parts to get the complete number, right? Okay, so this was the conversion from decimal to binary. Next, we can go with binary to decimal conversion. Okay, so it is again straightforward. So taking an integer, let's 10110 in binary is what in decimal. Okay, now this again, I told that each of these bits are having a certain weight. For example, this is 2 to the power 0, this is having a weight of 2 to the power 1, this is having a weight of 2 to the power 2, this is having a weight of yeah, if I delete this, yeah, correct, 2 to the power 3. So if it is 1010, so 2 to the power 0 weightage, 2 to the power 1 weightage, 2 to the power 2, and 2 to the power 3. So what is the decimal equivalent number for this 1010? So we can start like this. You can start like either you can start from MSB or LSB, both are fine. So suppose that I start from LSB. So this is 0 times its weight plus 1 times its weightage plus 0 times its weightage plus 1 times its weightage. This is 0 plus 2 plus 0 plus 8. This is 10 in, so this becomes 10 in decimal number. Okay, so the first weightage is 2 to the power 0, that is 2. 1, sorry, 1. The second weightage is 2 to the power 1, that is 2. The third weightage is 2 to the power 2, that is 4, and 8, and 16, and 32, like that. Similarly, you can go with the various conversions. I can give some numbers to practice for. 101 is what, and then 11111, let's say, is what, in, or 101010101 is what, in, or 100000000 is what in decimal. For this, we can easily determine this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 4, 5, 6, 7, 8. So this is having a weight of 2 to the power 8. So this will be equal to 1 into 2 to the power 8 plus all zeros. So 2 to the power 8 is 2 to the 4 to the 8 to the 16 to the 32 to the 64 to the 128 to the 256. So this would be equal to 256 in decimal. Okay, so you can do this conversion like this from binary to decimal, right? What about the fractional part? Okay, again we can have the fractional binary number. So let's say 0.1101 and binary is what equal in decimal number system. So in this, the weightage is, this is having a weight of 2 to the power minus 1. Okay, this is having a weight of 2 to the power minus 2. This is having a weight of 2 to the power minus 3, and this is having a weight of 2 to the power minus 4. So now you get what to do. So this is 1 into its weight plus 1 into its weight plus 0 into its weight plus 1 times its weight, and you add all these contributions. 0.5 plus 0. So 1 by 2, 1 by 4 is 0.25 plus 0 plus 1 by 16 is 0.0625. Check if the calculation is correct. Check. Okay, and this would be 0.8125 in decimal. Okay, similarly you can practice some more conversions. So for example, 0.111 in binary is what in decimal. Do this. 0.10001 in binary is what in decimal, or we can combine, and I can 1011.111 in binary is what in decimal. So for this, do the calculation separate for this integer part and the fraction part and combine them, okay, with a binary radix point. That will give the complete number, right? Okay, so again we can have different number. We have actually different number representations apart from binary and decimal. Okay, so like we have something called as octal number, representation. Okay, so it is having a base of 8, as this word suggests. Octa means 8. Okay, so total number of digits in the digit set is actually equal to the number of base, that is at 8, and the digit set is 0 1 2 3 4 5 6 and 7. Okay, so in this case the radix point may be called as an octal point for this octal number system, and this is also a positional number system or a weighted number system. Okay, also a positional number system, that is weight of a digit is defined by its position within the number. Okay, so we can have again the conversions between these different number systems, that is from decimal to octal to binary. So for example, we can have this conversion. I want this 879 in decimal to be converted into octal. Okay, so this decimal number can be converted into an octal number by simply again following the same rule that we did it for binary. So in this case we will divide it by 8 continuously and collect all the remainders, and we will continue till the remainder becomes smaller than its base, that is smaller than equal to 7. Okay, not equal to, actually smaller than 7. So we can perform this operation here, 879. So let's divide it by the base, that is 8, and so 8 times 109 would be 872, and the remainder would be 7. Again 8, so 1 3, the remainder here would be 5. 8 1s are 8, again remainder is 5. Go in this direction. Okay, and the number would be 1557 in binary, not in binary, that is in octal number system. Okay, similarly we can perform the we can do the conversion for the fractional part. Okay, so let's take one example for this also. 0.125 in decimal is what in octal? So 0.125 times 8 would result in 1.00. Carry is 1. We can stop here because we have obtained the fractional part is 0, so we can write at 0.125 in decimal is actually equal to 0.1 in octal. Okay, so take some questions for practice. 979.2 in decimal is what in binary? Then let's say 1000 in decimal is what in binary? 7894 point let's say 208 in decimal is what in binary. Okay, so we have seen the octal to decimal, sorry, decimal to octal representation here, that is decimal to octal. Now the reverse is from octal to decimal. How can we perform the reverse thing? So for example 753 in 8 is what is the value in with radix 10 or in decimal. Again the process is similar. We can write 753 and multiply with the individual digit weightage, that is 8 to the power 2 plus 5 8 to the power 1 plus 3 times 8 to the power 0, and this will give us 491. So we can write that 753 in octal is actually equal to 491 in decimal. So you got the idea, right? So practice some questions, that is evaluate 0.235 265.731 okay into evaluate these numbers into equivalent decimal numbers, or convert these numbers into equivalent decimal numbers. Okay, you can practice as many numbers as possible, so that will actually increase your confidence. So we can also have conversion between octal and binary. Okay, octal to binary conversion. Okay, for example for this we have to understand that each digit of an octal number can be represented or is represented by 3 binary bits. So one octal bit can be represented by 3 binary bits. Okay, so for example we can have like octal number and the binary equivalent number. We'll start from 0 1 2 3 4 5 6 and 7. 0 can be represented by 0 0 0, would be 0 0 1, this 2 would be 0 1 0. You can verify these values. 1 1, 4 would be 1 0 0, 5 is 1 0 1, 6 is 1 1 0, 7 is 1 1 1. So knowing these values, okay, we can, the tasks become very simple. So for example 452 in octal is what in decimal. So the idea is to replace each of these octal digit by its binary equivalent, and the number is there. 4 is actually 1 0 0, 5 is 1 0 1, 2 is 0 1 0, and this will be its equivalent binary number, right? So the task is very simple, so you can practice. 0.275 is what equal to in binary. You can have 746.421 in binary. Okay, if you can also do this conversion by different methods, but this is one of the most straightforward method. So for the fractional part also, you can replace just by its equivalent binary numbers. Okay, to get the direct conversion, to perform this conversion directly from octal to binary. So the next thing is how to convert a binary number into octal. Okay, now the binary numbers are converted into octal numbers by making a group of 3 binary bits, because we had seen that each octal number can be represented by each octal digit can be represented by 3 binary bits. Okay, so we make a group of 3 binary bits and replace those groups by their equivalent octal digits. So for example, let's say 1 0 0 0 1 1 1 1 0 in binary is what in. So we can group them. Let's say I group like this: 3 3 3. This is 1 1 0. This is actually 6. This is 3, and this is 4. Okay, so it becomes actually 436 in octal. One more example: 1 1 1 0 1 0 0. Group of 3. So group of 3, this one is left alone, so we can put 2 zeros in the starting. It will not change its value. Group of 3. Okay, this is 4, this is 6, this is 1. Understood? So this will come out to be 164. Fractional part: 0.0101, then let's say 1 and 1 in binary is what in octal. Again, do the grouping, perform the grouping. Start from the radix point. So we start from here, start the grouping from here, this bit itself, this one, this one, this is 2, this is 7, right? So it becomes 0.27 in octal. 0.27 in octal, right? What will you do if last, let's say last one is left without making a proper? Let's say if I had something like this: 0.01. Grouping requires 3. One bit is missing. So what will you do? Will you add a 0 here or not? Will you add a 0 here or not? Think about it. What to do for this type of conversion, this type of questions. So note down some questions for conversion. Say 100 10111 is what in 0.011 0.011 0101, then let's say 1011, then 0111, then 0110101. Okay, so with this the conversions between decimal and octal and binary is over, and the similar process can be performed with hexadecimal number systems also. So I will skip hexadecimal number. I will skip the conversion between decimal, hexadecimal and binary, okay, because the steps would be same as that of similar as that of the conversions between decimal, octal and binary. The only difference would be about the radix here, which is actually equal to 16. So the base is 16 here, as the name suggests, hexadecimal 16. So it also suggests that it is having a total number of 16 digits in the digit set. What is the digit set? Complete 0 1 2 3 4 up to, it will go up to 9, then 10 11 12 13 14 and 15 are the total 16 digits, but it will be confusing to use 10 11 12, as 12 also means 1 and 2. So whether it is 1 and 2 or 12, how to separate them? So for this reason, 10 is represented by capital A, 11 is capital B, 12 is capital C, 13 is capital D, 14 is capital E, and 15 is capital F. So the digit set is 0 1 2 3 4 up to 9, and then A B C D E F in capitals. Okay, so here the radix point is known as the hexadecimal point, right? And this is also a positional number system, that is the weight is defined for each digit in the number, and this is one of the most commonly used number system in microprocessors. Okay, so very important number system, actually one of the most commonly used number system in microprocessors. Okay, so I will give a table. Which will help you in the conversion between different number systems by binary. Okay, so decimal, let's say 0 and 1. In hexadecimal it will be same up to 9 4 5 6. Oh, sorry, this is 2 3 4 5 6 7 8 9. In hexadecimal also this will be same 0 1 2 3 4 5 6 7 8 9. But here in the case of binary numbers, the equivalent numbers will contain not 3 bits as it was the case for octal number system, but rather it will contain 4 bit. Okay, because the maximum bit, that is 15, can be represented by 4 bit. So each of these hexadecimals 0 will be 0000 in binary, 0001 in binary, 2 is 0010, 3 is 0011. Do not miss these initial zeros. Okay, you have to keep on carrying these initial zeros. Okay, 0100, 0101, 0110, 0111, 1000, 1001. Okay, now in decimal it will be 10, 11, 12 and 13, 14 and 15. In hexadecimal there will be capital A, capital B, capital C, capital D, capital E, capital F, and this will be 1 0 1 0 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1. Okay, right. So this table can be taken as a reference to perform the conversion between decimal to hexadecimal to binary to octal also, because we know the conversion table between decimal to octal and binary. Okay, so you can here you can write the equivalent equivalent octal number, and then in besides the equivalent binary number for that octal number representation. And remember that the octal number representation in binary will contain 3 bits, but the hexadecimal numbers in binary will consume 4 bits. Okay, and you have to use this capital A, B, C, D, E, F wherever they come. Do not hesitate to write these alphabets. Okay, so some of you might think that why to use alphabets, is it will look different. Okay, it will look different, but they are having their own number value and number value, face value, right? For example, just to omit any doubt, I can A to 3, let's say in 16 is what in decimal. So A 2 3 is a hexadecimal number. Okay, it can be written, the face value of A is actually 10 and its weightage is 16 to the power 2. Next is 2, the weightage is 16 to the power 1. Next is 3, the weightage is 16 to the power 0. So it becomes 2595 in decimal. Okay, so you will write the corresponding alphabets if it comes, and for calculation you will use the face value of that particular alphabet. For example, A is actually equal to 10. Similarly, D will be actually equal to 13. Okay, and so on. So perform the conversions between, or practice the conversions between decimal to hexadecimal to binary and then to octal number system. Okay, anything can be asked? Right. Okay, so if we go to your syllabus, for digital portion, I think yes, module 4 today, binary numbers we have done. Okay, signed binary numbers I will do. Okay, this one I will do. signed binary numbers important. Then decimal to binary, binary to decimal conversion is done, is over, right? So these four portions are over. This one, this one, this one, this one. Then hexadecimal number systems over, and apart from this we have also seen the octal number system. So we are left with this signed binary numbers. Okay, and then we will come to the arithmetic of binary numbers, that is binary addition, subtraction, multiplication and division. Signed binary numbers, so we can cover this portion today itself. Signed binary numbers. Signed binary numbers. Okay, so this is actually used for giving sign. For example, in maths we use plus and minus signs for giving positive and negative values. Okay, positive and negative values. Similarly in binary also, binary numbers also, we use, somehow we have to give the signature, or we have to represent, we have to say that whether the binary numbers are positive or negative. Okay, and it is not possible inside microprocessors to feed with actual positive or negative numbers, negative sign. So for this reason some alternative methods are adopted. In maths we use plus and minus signs for representing positive and negative values. Okay, but in computer hardware the bit, okay, itself is used, or we can write the bits itself are used for representing the sign, representing signs. So the bits associated at MSB positions, that is the at the most significant bit positions, will decide about the magnitude, not magnitude actually, will decide about the sign of the number. Okay, so we can have two, actually we can have unsigned and signed numbers, unsigned and signed binary numbers. So these unsigned numbers are always assumed to be positive numbers, but when we need to deal with negative numbers also, then there we adopt this method or this concept to represent positive and negative numbers. So this unsigned number consists of only positive number, but here you will find both positive and negative numbers both. So under signed binary numbers there are certain methods, certain numbers codes we can say, which are used for representing signed numbers. So the first method is sign and magnitude method. The second method is ones complement, ONES or ones. The third is twos complement. You can write like this, twos complement method, and we will see these methods. And then we can have excess k, also called as offset binary methods. Okay, and there may be some other methods, but these are the most commonly used and one of the four best known methods for representing signed numbers. Okay, so I'll start with this first one, that is the sign and magnitude. Sign and magnitude representation. So for this I will switch to here. Look at here. Like I said, we have unsigned and signed numbers. Okay, so unsigned numbers are contain only magnitude of the number, so they contain only magnitude of the number, they don't have any sign, so they always signify the positive number. So negative numbers cannot be represented by unsigned numbers. Okay, so that means all unsigned binary numbers are positive. So as in decimal number system, the placing of positive sign in front of number is optional for representing positive numbers. So therefore all positive numbers including 0 can be treated as unsigned numbers. Okay, if positive sign is not assigned in front of the numbers. So by default, whether we assign a positive sign or not in decimal number system, we assume that the number is positive. Okay, so they can be treated as an unsigned numbers even if a positive sign is not associated in front of those, right? But when we have to incorporate the negative numbers, what to do? And it is generally the case for most of the time we cannot have the calculations without having negative numbers. So signed numbers contain both sign and magnitude of the numbers. So this is important. This contains both sign and magnitude, and this contained only magnitude, right? So generally the sign is placed in front of the number. Generally the sign is placed in front of the number, in front of the number. So we have to consider the positive sign for positive numbers and negative sign for negative numbers. Straightforward, right? So therefore all numbers can be treated as signed numbers if the corresponding sign is assigned in front of the numbers. So we'll have to specify that whether this is a signed number or unsigned number. If we tell that this is a signed number, then in that case we'll have to take into account the respective sign of that particular number also. Okay. Okay, right. Look at here. So for example, the first we were with sign and magnitude. So this is the representation for sign magnitude number, and this is normal decimal number. So let's start from here. For plus positive 0. Okay, in sign magnitude what happens is that the first bit the first bit the first bit first bit, which is MSB, the most significant bit, will tell about the sign of the number, the sign of number in sign magnitude number system. Okay, 0 means it's a positive number, 1 means it's a negative number. So this is 0 and 0 0 0, so it's a plus 0. Okay, now this is, look at here, plus 1. The first bit is 0, it means that it is a positive number, and what is its magnitude? The magnitude is given by the next 3 bits, that is 0 0 1, which is equal to 1. Okay, plus 2. 0 means positive, and the value 2 is actually 0 1 0. Plus 3, the value is 0 1 1, which is actually equal to 3, and this is a positive number because the first bit is 0. Similarly, plus 7, 7 is 1 1 1, and the first bit is 0, so it is plus 7. So this 0 is for signifying plus, and these three ones means it's a 7. Okay, do not look at these two tables right now. We are just dealing with our signed magnitude number system right now. So I hope this is clear here. Now we can go and see the negative numbers in sign magnitude. Negative numbers in sign magnitude. Okay, so look at here, -1. So this 001 is actually the value 1, and a 1 at the MSB indicates that it's a negative value, negative number. Okay, -2, 1 is for minus, and 010 is magnitude -2. -4, this MSB at 1 is for negative sign, and 100 is actually 4. Similarly, -6 and -7. Okay, so the first bit at MSB decides whether it's a positive or negative number, and the next 3 bits, or the next bits after MSB, will decide the value. It can be 3-bit, or it can be less, or it can be more. Okay, so for representing between 0 and 7, it would be a total of 4-bit. Okay, when we go from 0 to 15, okay, it will be a total of I think 5-bit. 7, 3, 4, 16, 4, yeah, 5-bit, right? So this is how we decide the value of a number under sign magnitude number system. So just for repeating, sign magnitude number system. For example, if the number is, let's say, 1010 in sign magnitude, then what is its actual value? The first bit will decide that it's a negative value, and the rest 3 bits will decide its value, which is 2. So it is -2. So this is actually -2 in binary. Let's say 1 1 1 1. This is 1, so it is minus, and this 1 1 1 is 7, which is okay. Now tell me what will be this 1 0 1 0 1, then yeah, 0 in sign magnitude. The first bit sign, so it's a negative number. The rest all bits will decide its magnitude. So this is 1 0 1 0 8 to 10. So this is actually equal to -2. Okay. Okay, so okay, we can have, let's say, 0 1 1 1 1. What is this? 0 is for positive. 0 indicates positive, so it's a positive number, and the value is this one, which is 15. So this is a +15 in binary. Okay, so this is how we represent numbers with sign in sign magnitude number system, right? So this we have seen. Okay, and then we will see these methods we will see: 1's complement, 2's complement, and excess in the next class. Okay, so I will stop here for this class.